is Jacob Cady, and this is our lab video report for lab number 5, recycling of aluminum. The purpose of this lab was to prepare a sample of potassium alum from aluminum and to determine the percent yield. Background on this lab, aluminum is a pretty reactive metal. It is well protected by a thin layer of aluminum oxide, and it reacts slowly with acids and dissolves quickly in bases. So some materials we used here, we used an aluminum scrap, some scissors, a 250 ml beaker, KOH, H2SO4, a 50-50 mixture of alcohol and water, and a filter flask, and a Buckner funnel.
For the procedure of Lab 5, we had to accurately lay out 0.5 grams of aluminum scrap, cut into small pieces about 1 to 2 millimeter squares, and put the pieces into large 200 to 250 milliliter beaker. The aluminum scrap we cut off was exactly 0.5 grams. In the fume hood, we carefully added 25 milliliters of the 1.5 molar KOH solution. So our volume is 25 milliliters. We heated the beaker gently over an open flame or on a hot plate. Large quantities of H2 will be evolved. H2 is explosive, so continue heating approximately 30 minutes until the aluminum is completely dissolved and no fizzing around each piece. There may be some impurities or black specks which do not dissolve. If the volume drops below half the original volume level, add distilled water from your wash bottle to bring back to about 2/3 the original volume. This will help reduce splattering. Using your tongs, remove the beaker from the heating unit. Use a glass rod to remove small pieces of solids. Our observations for this was that it changed color from a dark gray. It was not clear, it was cloudy, it was steaming, and there was bubbles. At the 11-minute mark, nothing more happened. Then we seen a gooey participant. At 20 minutes, no bubbles. It was cloudy, gray-brownish solution. Volume now is approximately 50 milliliters. Then we prepared a piece of filter paper by folding it into quarters and placing it in the funnel. We wetted the paper with a small amount of distilled water to ensure a good seal at the top. Place the funnel over a 250 milliliter beaker, which will serve as a vessel for collecting the filtrate. While the liquid is still hot, pour it into the funnel and collect the filtrate. Rinse the reaction vessel with 2 portions of approximately 3 milliliters of deionized water each, and pass these through the filter as well. Discard the filter paper and save filtrate for the next step. The mass of the filter paper and the watch glass was 44.28 grams. We noticed a white precipitant formed. In order to remove the insoluble solids, filter hot solution through glass wool or filter paper. Cool the solution at room temp for 5 minutes, and then place it in an ice bath to cool further. While continuously stirring, slowly add 9 molar of H2SO4 until pH paper shows that pH is about 1 to 2. A volume of 2 to 5 milliliters of acid may be required. Large lumps of AlOH3 may appear initially, but these should be redissolved upon further acidification. Heat gently for at least 10 minutes at 60 degrees Celsius to 80 degrees Celsius. Do not boil, or until all the AlOH3 dissolves. Check the pH and add more 9 molar H2SO4 if the pH rises above 1 to 2. But do not heat more than 20 minutes. A clear solution should result. Remove from heat. Cool in an ice bath for about 20 minutes to form crystals of the potassium alum compound. Collect the crystals by vacuum filtration using a Buchner funnel and a filter flask. Transfer your alum crystals by swirling the liquid and crystals in your beaker and pouring the resulting suspension into the Bickner funnel while applying suction with the vacuum aspirator. Use a spatula to transfer as much as possible of your remaining crystals. To complete the transfer of your crystals to the filter, you will use some of your filtrate. Break the vacuum by removing the hose from the side arm of your flask. Remove the Bickner funnel and pour the filtrate into a small clean beaker. Replace the funnel, reattach the hose, and reapply the vacuum. Using small portions of your filtrate, transfer the remaining alum crystals for the reaction vessel. Onto the filter. Finally, wash the crystals in the funnel using several small 2 ml portions of your filtrate. Your alum product is still a bit wet at this point. To remove excess water from your crystals, use a disposable pipette to add slowly the 10 ml of cold methanol prepared during the previous step. Do not attempt to collect these crystals. Then, remove the top part of your funnel. You can pop it off from the remainder of the plastic funnel. Transfer the filter paper and your crystals to a watch glass and allow the alum to dry in your drawer until the next lab period. Determine the mass of your alum crystals. Transfer your crystals to a glass vial and label it with your name, the formula, and the mass. Enter the mass in your notebook. The mass, when we came back to the lab the next period, was 46.20 grams of the alum crystals and the watch glass.
So for the calculations portion of the lab, as you can see in number 1 here, we had the mass of our watch glass with the paper and the crystals was 46.20 grams. The mass of the watch glass and the paper only was 44.28 grams. So we subtracted that, and we got 1.92 grams of aluminum product. In step 2 here, we were calculating the number of moles of aluminum we had. We had 0.5 grams of aluminum. The molar mass of aluminum is 26.98 grams per mole, giving us 1.85 times 10 to the negative second moles of aluminum. In step 3, if you take the product, which was KAlSO42 times 12H2O, there's 1.85 times, there's 1 mole in aluminum, or of aluminum in there, therefore it gives us 1.85 times 10 to the second moles of the product, and the same as the mole of aluminum. Next, we found the theoretical yield, which we took the number of moles of our product and we times it by the molar mass of our product, which is 474.4 grams. That gave us 8.78 grams of aluminum product for our theoretical yield. After that, calculating the percent yield, we took the amount we actually had, which was 1.92 grams of aluminum product, and we divided that by 8.78 grams of aluminum product, times it by 100 because we're working with percents here, and that gave us about 22% for our percent yield. Lastly, here's our balanced equation. That gives you 2 aluminum solid plus 2 KOH aqueous plus 4 H2SO4 liquid plus 22 H2O. And that yielded you with 2 KLaSO42s times 12 H2O solid plus 3 H2 gaseous. Some possible errors that could have occurred during this lab. The beaker actually boiled over while we had it on the hot plate. That could have caused some loss of mass. We could have had some miscalculations, or potentially a loss of mass upon filtration. We could have lost some of the crystals, therefore it didn't mass properly, skewing all of the data set, so it would change our percent yield and our theoretical yield. Next time around, if this lab was to be repeated, we would just have to make sure to be more careful while boiling, and definitely make sure it doesn't boil over or anything, and make sure that we don't lose any crystals when we go to mass it at the end, which completely changes our entire data set.